Special greetings to my supervisor, Dr. Chiu Chan, and my examiner, Mr. Rajan. I am Bong Yun Ping at 2395, a Year 4 student from Computational Science major. Today, I will be presenting about my final year project. The title is AIot-based Smart Surveillance for Real-Time Behavioral Detection. Here is the outline of today's presentations. It mainly consists of 3 parts, including the Chapter 1 Introduction, Chapter 2 Literature Review, as well as Chapter 3 Methodology. The first part will give details of projects such as the background study, objective, project scope, significance of project, and expected outcomes. Besides, the second part will review suspicious behaviors, compare the differences between the models used, and reveal the academic gap related to IoT architectures in security framework. And the third part will give explanations regarding the 4 phases used in rapid application development methodology. To start, let's have some introduction to know the background of surveillance system. Despite having the cameras everywhere, the traditional surveillance are largely inefficient. A research shows that over 90% of CCTV footage is never actually viewed in real time. This is primarily due to the human factor, as the security guard's focus tends to drop sharply after just 20 minutes of monitoring a screen. And because of this, the suspicious behaviors, which are defined as any deviations from normal movement patterns, often go unnoticed, and sometimes the behaviors are hardly to be spotted out directly. Hence, relying on the manual detection is simply too slow to prevent incidents before they happen. This project addresses the problem by addressing an AI and IoT integration. We are shifting the paradigm from the passive recording to an active and automated detection. By using the intelligent algorithms, the system can provide a real-time alert for rapid response. Ultimately, this is about the campus safety. Our goal is to protect institutional assets as well as the campus community by reducing response lag through the power of intelligent automation. In this project, there are 3 objectives. The first objective is to design an IoT-based smart surveillance system that can detect suspicious activities. Secondly, the solution needs to integrate the AI algorithm for behavioral recognition. And thirdly, it has to develop real-time alert and monitoring dashboard. Now, let us define the boundaries of this system. Firstly, it's about the core hardware. The system is built on an edge-level processing architecture using a Raspberry Pi, camera module, and a physical buzzer for instant alerts. And secondly, it's about the target behaviors. We are specifically focusing on 6 critical behaviors, which includes loitering, trespassing, fighting, falling, running, and camera tampering. And thirdly, it's privacy-centric. It's a key feature of this design. We secure the environment through the behavioral analysis without any identity tracking or facial recognition. And lastly, the prototype is specifically optimized for the campus-like settings. To remain feasible, certain elements are out of scope, such as the multi-camera coordination, large-scale cloud integration, allowing the system to remain a fast, responsive, and localized unit. Moving on to the significance of this work. Why does this IoT system matter? First, automation. We are solving the human fatigue problem. By providing 24 hours, 7 days active monitoring, the system ensures that the security never takes a break or loses focus. Second, rapid response. It's not enough to just record an event. Our system provides real-time alerts through a physical buzzer and a digital dashboard, allowing the security to intervene immediately. And third, it's about privacy and ethics. Unlike many modern systems, we prioritize the security with the identity tracking. By focusing on the behavioral analysis rather than the facial recognition, we protect the community's privacy. And fourth, economic value. We are proving that high-performance security does not require a massive budget. By using a low-cost hardware like the Raspberry Pi, this solution is accessible for any institution. And finally, scalability. This project serves as a foundational prototype. It can easily be expanded into a large smart campus initiative in the future. By the end of this project, the goal is to deliver a fully functional AIoT prototype. For the hardware, it's a standalone unit powered by Raspberry Pi that performs all processing at the edge. From the side of the intelligence, the system will provide real-time identification for 6 key suspicious behaviors, as well as recognizing human objects and specific help signals. Furthermore, for the response, a dual alert system will be built to provide immediate physical feedbacks through a buzzer and a visual monitoring via the web dashboard. And for the result, it will provide a validated, privacy-focused security solutions that is both cost-effective and specifically optimized for the campus environments. Before we look at the how, we must understand the what. We have categorized 6 key behaviors that indicate potential threats on campus. Firstly, it's about loitering and trespassing. These are often precursors to crime. A person wandering without purpose or entering restricted zones poses a high risk of theft or security breaches. Besides, when it comes to fighting and falling, these represent immediate physical emergencies. Whether it's aggressive violence or the medical collapse, the system is designed to detect these sudden changes in human posture to save critical response time. Furthermore, running is also dangerous. In a hallway or quiet campus area, high-velocity movement often indicates a panic escape or someone being chased. And finally, we detect camera tampering. If someone's block or spread the lens, the system will treat it as a high-priority alert, as this usually happens right before a crime is committed. To choose the right model being deployed in this project, we conducted a technical comparison of existing AI methods. While CNNs are great for static poses, they cannot model how actions evolve over time. Hybrid CNN LSTMs and graph models offer excellent temporal analysis, but they are far too slow for Raspberry Pi and require massive computational power. And this led us to choose YOLO. It provides the best balance for our needs. It's a single-pass network with low complexity and excellent IoT stability. Unlike the others, YOLO is designed specifically for edge devices. It allows us to achieve real-time object and pose detection with optimized RAM usage. This choice ensures our system remains fast and responsive on-site. To justify our approach, we analyze current IoT security research to identify critical gaps. First, the detection scope. In many existing systems, they only focus on simple tasks like face or intrusion detection. Our project addresses the lack of complex multi-behavioral recognition like falling or fighting. Second, the semantic gap. While the previous frameworks can flag unusual events, they lack detail. We identify a clear need for semantic-rich labeling to ensure accurate responses to specific actions. And third is about latency and bandwidth. While some research highlights that cloud centralized models are computationally expensive and slow, and this justifies our use of edge-based AIoT to ensure an instant and real-time alert. Finally, it's about the contextual gap. We found a significant lack of surveillance framework tailored specifically for the unique environment of smart campus security. To build this system efficiently, we follow the Rapid Application Development Model (RAD), which consists of 4 integrated phases. For the first phase, requirement planning, we begin by creating functional and non-functional system requirements and justifying our research through a deep literature review. Then we go to phase 2, user design. We translate those requirements into technical blueprints, which include the creation of DFDs, ERDs, and dashboard wireframes, which are validated through supervisor feedback. And thirdly is construction phase. This is the development of a full-scale prototype. We integrated the hardware, optimized the AI inference engine, and built a real-time alert dashboard. And last phase is cutover. We evaluate the system through the performance testing to verify the stability of real-time alerts and the accuracy of our detection. To ensure the system is both robust and practical, the functional requirements have been categorized by priority. Firstly, the critical requirements are the core pillars of the system. They include continuous real-time pose estimation and the detection logic for the behaviors, including the loitering, trespassing, fighting, running, and the camera blocking. Crucially, the system must push the instant notifications to the dashboard and activate the localized audio buzzer without delay. For the essential requirements, this focus on the system administration and usability. This includes a low latency live stream, historical instant logging for later review, modular behavior toggle, system event logging, and a secure user authentication portal to restrict the system access. For the optional features, It also planned for the future scalability, such as statistical data visualizations for the trend analysis and the ability to export the incident logs as a CSV or PDF reports for the official documentation. While functional requirements describe what the system does, non-functional requirements define how well it must perform to be effective in a real-world campus setting. First is about performance. To ensure real-time safety, the system must maintain an inference speed of 5 to 8 frames per second, with a total alert response time from detection to buzzer of less than 1.5 seconds. Next is about reliability and accuracy. The prototype is designed for operational stability for at least 4 continuous hours without crashes, and our heuristic detection logic must achieve a success rate of exceeding 80%. Also, the web server must be accessible by devices connected in a local area network. Furthermore, it's about security and portability. We prioritize data integrity to prevent unauthorized log modification. Another design goal is edge autonomy, meaning that the system can still detect threats and trigger the local buzzer even if the external internet connection is lost. Besides, responsive UI design is also listed. Now we go to the second phase, user design. This is about the system and architecture design. First, let's look at the backbone of this system. The architecture follows a decentralized edge processing model. Instead of sending heavy video data to the cloud, all intensive tasks from data acquisition to data inference and storage are performed locally on the Raspberry Pi node. This significantly reduces the latency and bandwidth, following the best practices for the real-time analytics with low power consumption. Also, to ensure the system remains smooth and responsive, we utilize a decoupled architecture. By using an asynchronous producer-consumer pattern, we isolate the video ingestion from behavioral analysis. This prevents choppy video and allows the system to handle real-time data flow, even with the constrained resources of an edge device. Technically, the flow is straightforward. The YOLO v11 engine extracts the skeletal key points, which are then processed by our Python-based heuristic logic. If a threat is detected, the event is immediately logged into a local SQLite database. Finally, the system acts as a local web server using a fast API. It pushes the real-time alerts to the dashboard via the WebSockets and triggers the piezo buzzer through the GPIO pins for near-instant physical notifications over the local network. To wrap up the technical architecture, this flowchart illustrates the continuous operational loop of the prototype. First, data acquisition. The process begins with the camera module tree capturing the live frames, which are simultaneously fed into the dashboard for real-time monitoring. Then, it goes to AI inference. Each frame is processed by the YOLO v11 and post engine. This is a post where the model extracts the 17 unique joint key points for the post estimation. Then it's followed by the heuristic analysis. The coordinates of the 17 unique joint key points are passed into the custom heuristic logic. This is the decision-making hub of the system. Then, it comes with a conditional branching. The system will ask critical questions. Is a suspicious behavior detected? If no, the system will instantly loop back to capture the next frame, ensuring continuous surveillance. And if yes, the system executes a 3-punch response simultaneously. It triggers the GPIO buzzer for a physical alert, serve the incident metadata to the SQLite local storage, and transmit a real-time alert to the network dashboard. This repeat loop ensures that the system remains a responsive and always-on security unit. Here is a part related to the model design. We have chosen to use the YOLO v11 and post model. We select this nano variant because it is significantly optimized for high-speed inference on a resource-constrained hardware like Raspberry Pi 4B. This is a single-stage detector that performs simultaneous object detection and skeletal keypoint extraction in a single forward pass. It's critical for meeting our real-time performance goals. And as shown in the diagram, the model will identify 17 unique joint key points based on a COCO dataset. These coordinates provide the semantically rich data needed for our behavioral analysis. Rather than retraining a heavy network, we use this model as a post extractor. Then we apply our own heuristic logic or the threshold-based rules over these key points to classify the behaviors. This makes the system flexible and easy to scale without the need for expensive retraining. The model comes pre-trained on a CocoaPost dataset, featuring over 56,000 images. This ensures it remains robust across the various learning conditions and the environment found on the campus. If you look at the performance table, you'll see that it maintains high accuracy with only 2.9 million parameters. This efficiency allows us to achieve the low latency required for an effective edge-based security unit. Now, let's walk through the model inference pipeline, which we have specifically engineered to be a streamlined data flow for the Raspberry Pi architecture. For the stage 1, data acquisition, the raw frames are captured from camera module using the OpenCV library. Then it goes to stage 2, pre-processing. The captured frames are first resized to a lower resolution to maximize the frame rate and ensure smooth performance on the edge. We use a letterboxing technique to preserve the original aspect ratio, and this is vital to prevent image distortion that could lead to inaccurate keypoint localization. It's then followed by normalization to do the scaling, color conversion, and standardization. After that, the stage 3 inference engine. This is the most computational intensive phase. To overcome the hardware limits of the Raspberry Pi, we execute the model using the NCNN inference framework. By converting our model to NCNN format, the system can leverage the ARM Neon instructions to perform the mathematical operation in parallel across the CPU cores. This stage results in a data packet containing bounding boxes and 17 skeletal key points. And the stage 4 is heuristic analysis and confidence wefting. In the final stage, the heuristic engine calculates the metadata such as the zoom angles, velocities. To ensure the reliability, confidence aggregation strategy is used. This means that an alarm is only triggered if the behavior meets the logical criteria and also the average confidence score exceeds the specific threshold, so it can filter out the noise or the momentary occlusions. The next critical step is about the heuristic design. This is a rule-based logic that translates the raw coordinates into actionable security intelligence. For loitering, center tracking is used. If a person's torso center remains within a small radius for a set duration, an alert is triggered, while for the trespassing, point-in-polygon logic is employed. When an alert is triggered at the moment the anchor key points intersect a predefined region of interest. Then, to detect fighting, the system calculates the Euclidean distance between the individuals while monitoring for high risk or the elbow velocity, while the running is identified through temporal differencing, specifically monitoring if the pelvis velocity exceeds the normal working thresholds. For the falling, both the aspect ratio and velocity are analyzed. For example, we look for a sudden vertical shift in the body axis, like moving from 90 degrees towards 0 degrees, and is combined with a sharp downward velocity of the nose key point. Additionally, we detect the help signals by identifying the specific pose signatures, such as the wrist being raised above the eye level. Finally, we use a digital image processing DIP analysis to detect the camera tampering. By monitoring for a drop in the mean luminance or the Laplacian variance, the system can tell if a lens has been blocked or sprayed. To understand the logic behind the system operation, we utilize 3 levels of data flow diagrams. For the context level diagram, it provides the high-level overview. It defines how the system interacts with its external entities, including the environment which provides the visual data, the buzzer hardware for the physical alerts, and the security personnel who interact with the dashboard. For the DFD level 0, this decomposes the system into its core functional processors. The access is managed by the process 1.0, which references the D1 user data for the secret administrative credentials. Then, the branch starts at the process 2.0. It converts the video into key points, which are then analyzed in the process 3.0. This analysis is guided by the default settings and configurations, a flexible store for the AI sensitivity, and the confidence thresholds that can be adjusted through the UI to minimize the false alarms. And finally, the process 4.0. It will dispatch the alerts to the personnel and the buzzer based on the severity found in the event logs D3, while the process 5.0 will maintain the operational transparency via the system logs D5. Goes to DFD level 1. We have further decomposed the process 3.0 because it represents the core decision-making logic for this project. In process 3.1, the raw coordinates are transformed into geometric metadata like the joint angles and velocity. The process 3.2 will match the data against the predefined behavioral rules. To optimize the Raspberry Pi efficiency, we use the lazy validation in process 3.3, which is to calculate the key point confidence only after a potential behavior is identified. Then the process 3.4 will act as a final gatekeeper to ensure only high certainty detections that pass our confidence threshold are sent as real-time alerts. After that, here's the part regarding the database design and modeling. To ensure the system manages data reliably, we have designed a structured database consisting of 5 core tables: the users, the behaviors, the event logs, settings, and system logs. Our architecture utilizes one-to-many relationships to maintain the data integrity. For example, the users and the settings table are linked to the system logs using a user ID and config ID as a foreign keys to track who have made the specific changes. Similarly, the behavior table maintains a one-to-many relationship with both the setting and event logs. This allows the system to link a detected event back to its specific behavioral category and the configuration thresholds that were active at that moment. Every table is also assigned a unique primary key to ensure that every record is distinct and easily retrievable. To support this structure, we have also developed a detailed data dictionary, and this acts as our centralized technical guide, defining the exact data types, formats, and the constraints for every field. Now we go to the part of the interface design. The UI is designed to bridge the complex AI data with the initiative security management through 4 key areas. First is the left dashboard. This is a command center featuring a post-estimation stream, automated detection alerts, and a system health monitor to track the edge performance. Then, the event history is a centralized log for reviewing the incidents with built-in tools to visualize the trends or export the reports for documentation. Then is the AI configuration. This screen provides a granular control using the modular toggles and the sensitivity sliders to tune the logic and minimize the false positive. Finally, we maintain a detailed audit trail, categorizing the backend events by the severity for the rapid troubleshooting and accountability. Moving into the core technical development of this project, we have phase 3 construction. This phase follows a structured pipeline to transform our theoretical design into a fully integrated prototype. We begin with inference engine development, where the YOLO V11 model is optimized for the Raspberry Pi. This is immediately followed by the logic testing, where we verify if our heuristic rules, like those for the falling or loitering, are correctly interpreting the scattered data. Once the brand of a system is stable, we move to the database implementation using an SQLite to ensure the incident metadata is stored securely. Parallel to this is the dashboard development. It will create the user interface that the security personnel will interact with. Then, the system is configured for the local hosting on a Raspberry Pi. During the final integration, we bring the AI engine, the database, and the dashboard together into a single cohesive unit. So the phase will conclude with an integration testing, where we run the complete system end-to-end to ensure the hardware and the software communicate perfectly before moving to the final evaluation. This systematic approach ensures that every component is individually validated before being merged into the final design. Finally, we reach phase 4 cutover, where we move from development to rigorous system validation. Our primary validation is focused on the performance requirement, specifically the inference latency and alert response time. We also conducted the SOC test to verify the operational stability and the dashboard uptime over extended periods. To scientifically measure our heuristic accuracy, we also benchmark the system using 5 globally recognized datasets. For instance, we will use the KVL to validate the loitering detection during the bronzing intervals. Besides, the PETS 2009 is used for the trespassing, testing our raycasting accuracy in open space. For the high-stakes event like the fighting and falling, we utilize the UCF CRAM and URFD datasets to fine-tune our kinetic energy and the spine angle thresholds. Also, for the running, the Kesha action dataset is used for validating the isolation from the normal walking. This phase concludes with the successful handover of a fully integrated AIoT prototype validated for the real-time deployment in a smart campus environment. That's all from my presentation on the AIoT-based smart surveillance system. I would like to sincerely thank my supervisor and the examiner for your time and guidance throughout this project.